in terms of design, I love to always bring the 1980s design of yellow slides on blue slides, but honestly, today's goal is really just to get people to understand a little bit of the problem space that we deal with. So we've had a lot of really great discussions this morning. That first session really tried to bring in all these different factors. So my goal for today is to basically take you down one rabbit hole, basically call it a case study of how we deal with one particular problem. My specialty, decompression sickness, is also my passion. It ties a little bit to diving, but honestly, you don't have to be a diver. You don't have to even care about decompression sickness. The goal here is to see the path rather than the actual options. We're going to talk a little bit about some terms, exploration atmosphere, ethers, etc. If you have any questions, please interrupt. Just put your hand up, interrupt. I am going to try to condense a lot into one slide. And again, the idea is not to make you all decompression sickness experts. It's just to see how meandering one path can be and how trying to think outside the box helps. So we will take some cues from our design approach and try to make it a little bit more visually gratifying. But again, I'm coming from the medical side, so Inkscape is about as good as it gets. There we go. So I'll talk a little bit about what decompression illness is. There are papers out there. We have one where we talk about ebulism versus decompression, hypoxia, barotrauma. Basically, decompression sickness involves bubbles, usually nitrogen, in the body coming out. So if you are a diver, you probably heard of the bends or decompression stops. If you're not a diver, if you've ever opened a carbonated beverage, that's what we're doing. We're just opening that bottle. Do we open it slowly and keep everything in check? Do we open it too quickly, make a mess? Or as we'll see for Lunar EVAs, are we shaking that soda bottle while we open it? So the fundamentals are you lower pressure, that forms, that releases nitrogen from the body. So nitrogen is about 80% of our atmosphere. It's dissolved in the body. It doesn't really do anything other than just sit there until you lower the pressure. And that's, again, opening that soda bottle, bubbles come out, and those bubbles can cause trouble. We divide it into mild, severe, all of these different things. It doesn't really matter too much other than it's bad, and it can be not only incapacitating, it can be life-threatening or fatal.
Where are the bubbles occurring?
So everywhere in the body. So basically anywhere you have a tissue, you have liquid, you got nitrogen dissolved in there. So for those of you on the physics side, Dalton's law of partial pressure and Graham's law of solubility, that nitrogen sits in there. And so when you release that bubble, they come out. Now, if you think about it in the blood, they come up very quickly. You breathe them out through the lungs. If they're in the muscle, they're a little bit more deeper in the tissues. And if they're in cartilage, so bones, et cetera, where there's not a lot of blood flow, those bubbles are hard to get out. And so you hear about tissue compartments and half-lives. Without, again, getting too technical, there's basically different compartments that we model. And we say, hey, these bubbles are harder to get out than these other bubbles.
Can you say for the designers in the room that may not know why bubbles are bad?
So I can show it. So if you look at these bubbles here, you see this is what a normal heart looks like with a few bubbles showing up. And what you're looking at here is a very choppy video of a heart beating. And you'll see that some bubbles come up. If you open that soda bottle too quickly, you get all these bubbles in there. So what do those bubbles do? In the body, in the circulation, they don't do much. We both basically catch them in the lungs and we breathe them out. If you have a PFO, which is basically a little hole in the heart, you bypass the lungs. Now those bubbles go to the brain. Now you're basically obstructing blood flow and you can cause stroke-like symptoms. So again, you're throwing a bubble, you're blocking blood flow. It also doesn't make the body very happy to have gas interfaces going across the blood vessels. And so you get a lot of inflammation. And in joints where they're trapped, as they swell and they push on things, they can hurt because they're pushing on nerve endings, and it can also be incapacitating. In the spine, if you think you're pushing on a nerve, now that nerve is no longer optional, so now you can't walk anymore. So you might be basically paralyzed from the waist down.
So bad.
Bad stuff. And we also talk about the remoteness angle of this. So if you think about diving, sort of like the worst case example for diving is you're in the South Pacific somewhere, it might take 20 hours to get you home. On the ISS, we're about in that range already. We're about 24 hours to get somebody home from the ISS if they need to, say, call it off and say, we're going to come down. The ISS is not that far. It's about 400 kilometers, 250 miles from the Earth's surface. It's just it moves really fast. It's really about catching up and kinetic energy to get there rather than the distance. When we talk about the moon, though, which is our focus in our work, you're adding a factor of 1,000 to that. So it's not 240 miles, it's 250,000 miles. And so with all the orbital mechanics of getting to the moon, synchronizing orbits, et cetera, you're talking 10 plus days to get home if you needed to get home right away. Effectively, for many medical conditions, including decompression sickness, it means Earth is just not an option anymore. And that's something that's new to NASA. It's not something that we've really seen since the Apollo days. So when you have something bad, what do? You prevent, but then you also have to think plan B, what happens if you do have it? So you treat, and then how do you treat, again, in a lunar environment where you're not taking an ICU, you're not taking a hyperbaric chamber, you're not taking all the resources you have on Earth. So we'll talk a little bit about that. Now, when we talk about decompression sickness for space, a lot of people ask, well, is that like the diving one? 80% of the time it's absolutely true. 20% of the time it's the opposite, and that opposite usually kills you. And so our goal really is not just to understand decompression sickness, but also understand what parts of medical treatment that we know on Earth works for diving that we can use in space, and what we want to make sure we do the opposite. And we'll talk a little bit about how the things are opposite, but basically you can think of an EVA as spacewalk as diving backwards in terms of our decompression stress, and we'll explain that here quickly. I'm going to skip on what some of these dive profiles are, but just in terms of graphical representation, when you go diving and your low watch tells you to do a safety stop, that's something that we see in recreational diving. These dives look a little bit more like saturation dives. So this is what a dive to 300 feet looks like. And without getting too complicated or technical, you see that big red stripe goes deeper and deeper and deeper. That means longer and longer decompression times. And so we're talking about hours of pre-breathe and management of this, not minutes, like you might on a dive. So let's take a step back, and I'm going to run you through a really quick bit of physics as to what it means on the ISS right now to do a spacewalk. So if we manage here, on the bottom I have time, on the vertical axis I've got pressure. You can think of our atmosphere as 80% nitrogen, that's that big gray bar, and then 20%, 21% of oxygen, that's that green bar, right? So green is good, we need it to breathe. Nitrogen, that gray thing, doesn't really do anything other than just sit around. Now, if you add those together, that's our atmosphere, that's our total pressure. When we get in a spacesuit, we want to be at as low pressure as possible because we want to maintain flexibility of the suit. You don't want to be stuck in a Michelin Man balloon just floating around. And we talked earlier, right, when you lower the pressure, like if you're going up in an altitude, you can get hypoxic. So we want to make sure that we keep the oxygen there. So we're going to keep the green bar, get rid of that gray bar. So if we drop that, great, we've got an EVA. We drop it usually to about 4.3, which is just a historical number. But that gray bar, that nitrogen that's in the body, is trying to get out. And so all that nitrogen is basically forming bubbles. Again, soda bottle you've opened up too quickly, and you've got badness, decompression stress. We show it here with a red triangle that we're trying to get rid of. So how do we solve this problem? Well, actually, first, what does this problem cause? We talked a little bit about it, is bubbles. And so those bubbles grow over time. And so over the course of 1, 2, 3, 4 hours, you can get basically whiteouts like we're seeing in those pictures, which is bad. So how do we solve it? We breathe oxygen. We don't need oxygen at sea level. The space station is like being, again, at sea level. But what you need is not nitrogen. And so the not nitrogen gas we have is oxygen. And so what we do is we breathe pure oxygen, and that lets all that nitrogen come out of the body before we drop the pressure. And so now that big nasty red triangle is a lot smaller. So we managed to decrease our decompression stress significantly. But what we did do is now we've added an oxygen pre-breath requirement up front. When we finish the EVA, we go back to the habitat. That nitrogen is back there, but because the pressure is so high, we just squeeze any bubbles that are forming during that, and we basically solve the problem.
How long is a pre-breathe period on ISS for an EVA?
About 4 hours, and we'll talk more details about what it looks like. So when we look at these, red triangles and decompression stress, how do we actually model that? So we have a few different models at NASA. We use TR, tissue ratio models, and bubble growth index, where we basically numerically approximate the size of a bubble in this ideal tissue and how it grows over time. What's interesting is that even though that highest ratio of nitrogen happens up front, those bubbles take a long time to grow, and so they get bigger and bigger and bigger until we end the EVA. Now, decompression sickness, in terms of like people saying, ow, my knee hurts, so I can't feel my legs, that actually happens in between. So it happens usually in the 2 to 4 hour period range. And so again, these models are using different parameters, different time frames, and all of these don't always match the human perception of it.
Like, are your models assuming that your pre-breathe is done
Yep.
in the airlock? So, you know, someone's kind of taken out of commission and sitting in the airlock for 4 hours pre-breathing? Or are you taking the whole station down the night before to sort of
Yeah.
sleep so they don't have to be isolated during the pre-breathing?
So for this initial approach, we're just assuming you're breathing at 100% oxygen at sea level, so you're not changing the pressure. And then once you get in the suit, you drop the pressure. We'll talk a little bit. There are some ways you can do it. One of the ways we've used in the past is called Campout, where you basically partially depressurize the cabin, so you reduce a little bit of that green, so you get a little bit hypoxic, but a lot of that gray bar, so a lot less nitrogen, and you sleep there. The problem with sleeping in the airlock is there's no toilet in it, and so if you want to get out, now you have to put on an oxygen mask to make sure you're not getting all that nasty nitrogen from the rest of the ISS on board. And then you have this big long hose, and then you go across modules, you use the bathroom. Your body has to get on a mask too, because there's always 2 people going out the door. And then you go back to the airlock, close the hatch, drop the mask, and you've also been breathing pure oxygen, which is a limited medical resource. And we'll talk a little bit about what it looks like. Bringing it back to the diving world, right? The big difference is in diving, and one of these things is like, why is it not the same? Well, in diving, if you remember, if we use that analogy of gray and green bars, when you're diving, you're actually increasing the pressure as you go down. So if you're breathing air, you dive, now that big green bar gets much bigger, and then that big gray bar gets much bigger, but you're not forming bubbles, right? You're just putting nitrogen in the body. It's when you surface at the end that now you've come up quickly, and all that nitrogen that you picked up the bottom of your dive, that comes out. And so you see that it's post-dive where you see decompression sickness in diving. And so the management that you do in diving by doing a decompression stop is actually you just add stops at the end. So you basically track that red triangle on your way up, and that lets you get rid of the nitrogen without decompression stress. In space, you realize that because the stress is up front, you have to do your decompression stops at the front, which means if you went a little bit longer or a little bit different pressure or worked a little bit harder, you can't go back in time and change your pre-breathe. And so it's one of these things where you can't just fudge it as you go along. You have to commit to a particular stress. So again, prevention, prevention, prevention. We'll talk a little bit about exploration atmosphere in a moment, but also keep in mind the suits are also not the same. So we have the Apollo A7L suit worked at 3.7 psi. The current suit works at 4.3. Orlan, the Russian suit, works at 5.8. And the next generation suit we have goes anywhere from 4.3 to 8.2. And so we'll talk about what that means. We won't talk too much about the NBL, the Neutral Buoyancy Lab, which is the big pool, where we also do actually diving decompression sickness as well. But let's talk first, how do we manage all this decompression risk at NASA? So NASA is an engineer organization, so what do? You have a requirement. You always go to the books, and you have a requirement. This requirement, and I feel like I kind of own it, is horrible, because it basically, if you read it, is talking about the statistical incidence of type 1 versus type 2 with confidence intervals, et cetera, et cetera, et cetera. What it means, basically, if you condense the numbers, is that the more you test, the more risk you can endure. So you can actually, if you do something 10,000 times, you'll know it's 14% plus minus 0.1%, which meets the standard. So you could bend people basically every other EVA and still meet the standard. Not great. The other thing we do is, so we have a requirement. What do you do next? You test. And so NASA's been doing these tests for different decompression protocols for decades. These are basically the last 40 studies we've done since 1982. So that's when I was born. They've been going all the way through. We had a lot of tests. You see that green block PRP, pre-breath reduction program. That was to prepare for ISS. What we're doing now is preparing for the moon and Mars. And so we've basically spooled up all these new tests, and you'll hear the term exploration atmosphere. Now, we said we test with humans. Where do we do this? Basically in a big metal can. We call it the 20-foot chamber. It's 3 stories tall. And what this lets us do is simulate all these different atmospheres and environments. We'll come back to the 20-foot chamber here in a moment. But what I want to do is bring us back to all these different risks we're talking about and how do we sort them out. And so what we use is basically this DCS risk stool that we put together, and it has 4 big legs on it. atmospheric composition, pre-breath duration, suit pressure, and EVA workload. So we're going to go through each of these legs. Start with EVA workload. So how hard do we work during an EVA? So right now in an ISS EVA, this, by the way, is what your pre-breath looks like. So you're asking how long does it take it? You do all of that during the pre-breath. It's about 4 hours. Now you're not always on 100% oxygen the whole time. It's complex, and then you go out the door, and voila, you're floating around in space. As you see, the legs are really just an attachment point. Most of the work is done with your arms on an engineered surface. When we go to the moon, though, it looks a little bit different. So here's where I can get a little bit of audience participation. What are all these people doing? Any thoughts?
Walking.
Walking. That's a big one, right? Do we walk on ISS? No, right? The legs are just an attachment point. What do we use when we walk? We use big muscles, and we shake around that soda bottle, right? So you see that guy over there is walking. What are these guys doing?
Bending.
Yeah, bending, scrunching down, doing squats basically to pick up, or mess with something. They're banging, right? So we're doing shock loads, etc. And then this guy, I think he just lost the keys to the rover, so I don't know what that one is, but anyway, you're basically picking up, doing all sorts of stuff. And so we need to make sure we manage that. And again, very different from diving, right? When you're out on the moon, you're shaking that soda bottle when you have all the bubbles. So you're rolling around, tripping up, falling, etc. And these are all from the Apollo EVAs. Versus again, when we try to leverage undersea diving exposures, post-dive, when you're forming the bubbles, you're not shaking that soda bottle, right? Hopefully you're on the hammock, relaxing, post-dive, having a good time. What's really interesting, sorry?
So I think you're selling doing EVA as opposed to dynamic.
What's also really interesting is that the physics at play are quite different because of the pressure involved. So when you think about reducing pressure, right, you're changing orders of magnitude. And so when you lower the pressure, a twofold pressure change gives you a twofold volume change. And so when you go in diving, you have all these sort of bubble growths. And we run the bubble models for diving as well. And you see that you get all these bubbles, and this index gets you from 4, 6, 8 is bad in diving. In EVAs, we're getting to 20s and 25s because the bubbles just grow so much more because the pressure is so much lower. So again, we can't really pull diving data. We can try to match risk even with bubble growth, but again, an 8 to 10 size bubble, if we want to call it that in diving, gets you about 20% of the people bent. In EVAs, we're going to 2, 3, 4 times more exposure than that before we see the same DCS risks. So again, we have to test in the humans, and we have to simulate things correctly. So we use exercise. There's a lot of studies out there that went and looked retrospectively at exercise and saw that if you do exercises, and here what you're seeing is mLs per kilo per minute of workload. This chart, basically, you hit 100% DCS rate at 12. That's basically a gentle walk. And so when we're talking about walking with a 400-pound suit out of a crater, possibly carrying your buddy, it makes a big difference. And we see this also in some initial studies. If you're doing an ISS-like EVA, so you're not really moving, you might have no DCS, you do the same protocol, you'll get 20% DCS impact just by adding ambulation, so that walking part that we called out. So we basically match every activity we think we could do on the moon. We map a workload to it, and then we simulate it in our chamber. So our first floor of the chamber looks a little bit like a jungle gym, where we basically have people do all these different exercises. It's extremely boring. You basically do 5 minutes of one stage, basically call it high step, low step, cranking with your arms, etc. And every 15 minutes, you lay down on the cot, and we measure those bubbles. That's how we get those pictures that you saw earlier with bubbles in the heart. So that's great. We simulate the workload. We try to make sure we target the right amount of stress. But we know that EVA workload is a problem. So how do we fix EVA workload if we're stuck with a 400-pound suit? Well, we go look at those 3 other legs of that stool. So atmospheric composition, right? We heard earlier, hey, how about we just change the atmosphere we live in? Why do we have to be at 100% pressure compared to sea level? Can we work a little bit lower? For those of you who remember Apollo, they worked actually at about 1/3 of an atmosphere, 100% oxygen. Now, there are some issues with that, basically flammability. And so we can't just pull from ISS what we're doing now, and we can't go back to Apollo and do what they did back then. So we're basically stuck in something in the middle. And if we try to cram some of these different pre-breathe protocols, they just don't work. So if you have an ISS pre-breathe that takes about 4 hours to get out the door without shaking that soda bottle, and now you start doing it, now we're talking about a 7-hour pre-breathe. If you put a 7-hour pre-breathe before an 8-hour EVA every day on the moon, you're not getting the crew any sleep, rest, or anything. And remember, this is 2 people and they're both going out. On ISS, we have 2 people going out, but there's a third person that's basically helping them button up the suit, make sure all the leak checks are correct, adjust conch caps, etc. And so we need to fix it. And we fix this with exploration atmosphere. And so what we're doing here is we're going to play with our atmospheric composition. So if we think of pressure, again, on the y-axis, and now the percent of oxygen on the bottom, we know that we live in Earth, 21% oxygen atmosphere, so we've got this nice green line, and that's where the ISS or sea level is, where we are right now. So we know if we go up, you can get really goofy, really hypoxic, so we don't want to do that. We know if we go to the right and increase the oxygen percentage, we can catch fire. And so the idea is, how can we balance all of these different parameters? And so we say, well, we can go up a little bit, let's call it 4,000 feet, and that's our hypoxia limit right now. But more than that, we might get a little bit too goofy. So now I have to put oxygen in, so we start adding oxygen as we decrease the pressure, but then we get to our flammability limit. And so we draw the line. Initially we said, let's draw the line at 36%. Now this is, again, an engineered cabin. Things change, so we have a little bit of margin, 34%, and then we have 8.2 PSI. That's equivalent to about 16,000 feet. So think of driving to Pikes Peak, but then having a bit of a nasal cannula, so you're at 34% oxygen. That's what we're looking at. So we did that test. We used that chamber. So we have on the top floor, we have cognition testing to make sure people are not getting too goofy from the hypoxia. They're also eating HLS food to see if we can see what they're eating. By the way, if you see the clothing, they're not all inmates. It's actually, we're doing all this studies on volunteers, but that's basically a fire retardant material. For those of you who know Nomex, which is a fire retardant, that actually is only good to about 30% oxygen environments, so we have to use some fancier stuff here.
Are you modeling any women?
Yes. Actually, I have this question, like, for some reason, this is not even an EVA test, but these are all guys. We aim for 50% women in our protocols. We have, I think last time I looked, about 40% of our subjects are women. We also model VO2 and age, et cetera. So we do have age constraints as well.
Are the hats also for fire retardant reasons?
Yes, that was actually a compromise. Talking about compromises, initially they asked me to have all our subjects shave their heads before going in the chamber because hair is so flammable. And so I said, no, we can't send a bunch of shaved heads to the moon. That's not a good look for. That's not a good look for NASA. We can do better. So they said, well, take this wool cap and put it on everybody's head. So we had to put that as a compromise. But basically on the second floor, we have these boxes. They're 1 meter by 1 meter by 2 meter, basically pod hotel type habitats. Yeah. You can get out if you ask nicely. So we basically have a big can where we can simulate it. And what we do is we just simulate an EVA by changing the pressure of the environment. So people live in there 48 hours to equilibrate, get all those curves to go to neutral at this new environment. And then we simulate the depressurization of an EVA. So we talked about living at about 16,000 feet. The EVA pressure, that 4.3 PSI, is about 30,000 feet, 10,000 meters. Think of it at the top of Everest. So if you go to the top of Everest on oxygen, that's what you're doing during an EVA. The profile is basically do an EVA every other day, measure bubbles, look for decompression sickness. How do we measure bubbles? We use that ultrasound, which gives us those nice pictures, and we also use Doppler, which is basically a fancy stethoscope. We see how many bubbles we see passing through the images and how many we hear, and we also use it as a grade because we don't necessarily bend everybody, but we also want to know, are we really close to the limit or not? And then we basically look, how many bubbles did we see? How much decompression sickness? Do we meet that NASA standard we talked about earlier? So we did this study. We passed, mission accomplished, success. Unfortunately, They said, well, 36% limit, yeah, let's not do that on the moon. We're going to use 30% as a limit. So now basically back to the drawing board, again, trying to be nimble on our feet. They said, well, that red line, we're scooting it over to the left. So if we go from 36 to 30, we're pushing this little ball all the way up to here. So now we have a new exploration atmosphere, 28.5% oxygen, 9.6 psi. So off we go. Now we have a lot more nitrogen on board. So how do we fix that? Well, we're going to have to spend more time breathing oxygen to get rid of that nitrogen. So instead of 20 minutes, we're going to have to go longer. So we said, OK, let's try 90 minutes. So off we go. Same thing, 90-minute tests. We start the protocol. Unfortunately, we had a type 2 case. So there's a neurological case. So we had somebody that had loss of sensation, decreased feeling. Not good on the moon. On Earth, we can treat it right away, and so we pull the individual out, but we know 90 minutes is not going to work on the moon. So then we went to 150 minutes, 2.5 hours of pre-breath. Again, that's not great in terms of overhead. So we did that study. We saw a bunch of bubbles. We didn't see any decompression sickness. So we basically fixed our problem, right? We said, OK, if we're going to go to 28.5% oxygen instead of 34% oxygen, we'll just do 2.5 hours of pre-breath and we're done. Mission accomplished? Well, no, because 2.5 hours, still too long with our timeline. So they said, well, we have to fix that. So how do we fix that? Well, another leg we can turn here on this stool is our suit pressure. So we can basically change the pressure of the suit so that we're not dropping quite as much. And that basically means less decompression stress, so less pre-breath duration. So we tried with exploration atmospheres 1 and 2, 1 environment, 3, and then 4. We tried different suit pressure. So again, back to the drawing board, back in the chamber. We took the suit pressure up to 5.2 psi. 20 minutes should work. Yep, it looked like it worked on the first time round. On the second time round, whoops, more type 2 decompression sickness, neurological findings again. So not great. And we're seeing too many bubbles, so then we go ahead and have our alternate. We go for 50 minutes, so we're still under 1 hour of pre-breath, which is good. Not great, but at least we did that stuff, that work, and now we've managed to check that box. So that's great, right? We've solved our problems. We have everything done. Why does suit pressure work so well? You know, how can we go from 150 to 50 minutes? It's basically we're cheating on this graph. So instead of moving the line over this way by more pre-breath, we're just changing this here. But effectively, we're just making that red triangle smaller. And so that's what we're doing, right? We're just trying to get rid of that decompression stress. We're going to make that red triangle as slow as possible. So elevated suit pressure is great. So now we're all done, ready to go out the day. Unfortunately, if you look at the Artemis CONOPS, it's not 1 EVA, it's 5 EVAs in 1 week. We normally do about 5 EVAs a year on ISS. Now we're doing that in a week. And so you're going out every day. And so what happens when you go out every day? Well, yesterday's EVA means you've been breathing oxygen for 6, 8, 9 hours. And so that actually gives you a little boost, right? Now you're starting the day with less nitrogen. Maybe. We also have studies from altitude chambers that if you look at inflammatory markers, they go through the roof and stay that way for over 24 hours. And so we did a study in July where we basically did back-to-back EVA. So every day we were simulating an EVA. We drew some blood. Can we use any of the diving data? We tried. Repetitive diving was a big thing in the 1980s with people going on liveaboards and doing 4 or 5 dives a day. Nobody ever did that in space. Even on the shuttle where they had daily EVAs, most of the time there were 2 alternating teams. So the 2 individuals that were going out one day would actually have the day off and then go out the next day. So we don't have too much data on that. We simulated that actually in July. We'll be presenting this at next year's annual conference. Now, a higher suit pressure is great for decompression stress, but now we also have a stiffer suit. And so one of the concepts we're pushing, and we just did a test in November, we're looking at stepping down the suit pressure. So we start at high pressure, suit is a little bit stiffer, but then as we are breathing nitrogen and moving around and getting all that nitrogen out, we can give the crew a little bit of relief and lower that pressure. And that's what we call working pre-breath or step downs. And so
that's a quick question.
Yeah.
Is it the hands that's the problem?
Yeah.
The stiffness more than anything else?
More than anything else, it's the hands and the ability to grip. And so the idea is actually some of the data we have is when you're ambulating, so higher ambulation, more workload means you're actually off-gassing that nitrogen faster. So walking with oxygen is a way to accelerate it. And if you saw in the ISS protocol, it's called protocol, ISLE, in-suit light exercise. So actually exercising at pressure gets that nitrogen out, so that accelerates it. So we think walking out with a higher suit pressure gets rid of that nitrogen and actually counts as like bonus or extra pre-breathe. The problem is you need to open the hatch and load the tool cart and everything at the start of the EVA, so you do need some fine motor skills up front. And the idea is, can we sort of twist the knob as we do the EVA, so when you're walking, you can pressurize the suit. That actually supports the suit itself a little bit, so it decreases your work. But again, this is all with a suit that's basically just coming off the design board as we speak. So just as a quick recap, we basically started at our oxygen environment. We changed the atmosphere. We did some pre-breathe. We then dropped the pressure. We are playing with the pressure we changed, how long we do the EVA. We can even play with our step-down protocol. And then we also talked about how our cadence affects it. And then also, you could theoretically stop halfway through an EVA. So these are a bunch of different factors that we do. I'm going to just skip through these because this is getting a little bit more into the medical side. But PFO, that little heart, lets you bypass the lungs that normally filter out the bubbles. We've started actually looking at every astronaut. So the last selection, we actually had a PFO, not screening, but surveillance, because we're not selecting or screening astronauts based on their PFO status, but rather just being aware, going eyes wide open as to what is the risk that we're entailing. From diving, we know that about 30% of people have PFOs, but only about 6%. The bigger ones really matter in diving. We don't have any idea of what they mean in altitude exposures. Right now, current practices were to just don't ask. We're asking, we're looking, but we're not making decisions until we get the idea. Another thing that happens is we're living in a hypoxic environment. We do know that hypoxia basically makes the lungs squeeze a little bit more. That makes the pressure on the right side go up, which makes those bubbles cross over a little bit better. So again, it's one of these things that normally is not a problem, but when you're in a weird environment, hypoxic with bubbles in your bloodstream, not normal, that's a problem. Other things we need to look at are contingency cases. So we had this very nice graph, and then we have that red triangle disappear. But what if you have a hole in the suit, and now your suit partially depressurizes? Now you get another bump of decompression stress at the end when those bubbles are growing. So do you get bubbles skyrocketing or not? We don't know. We'll also talk about pre-breathe. So we talked about 150 minutes, 2.5 hours of breathing oxygen. Well, what if you have to come off that mask because either it gets bumped or you have to readjust something? Do you start all over again? Do you have to scrub the EVA? We don't know. The Air Force did a study back in 2010, and they thought 10 or 20 minutes of break would be nothing. They were seeing 84% decompression sickness in some of their cases. So again, big issue. And assuming we do get decompression sickness, how do we treat it? We do not have a hyperbaric chamber on the moon. This is what it looks like just for our ground testing. And again, this is just to show some of the different aspects and complexity of treating it. In space, we don't know how to treat it. We've never treated it. It's happened, actually, the only time it's been reported to have happened is by Michael Collins in his autobiography post-flight, when he said, yeah, he had some knee pain on Gemini 10 and Apollo 11. He was busy orbiting the moon while these two other guys were doing something on the moon on Apollo 11, so he decided just to load up on aspirin and suck it up, and then talked about it in his autobiography. So that's all we know. On shuttle, there have been no reported cases, but again, the suit is not a very forgiving environment. It's not a nice comfy bag. It's more like hard points and pain, and so it's very hard to distinguish necessarily if it's suit pain versus DCS pain during an EVA. Now, we're talking about the suit as a pressure bag, right? Now, a hyperbaric chamber, which is how we treat decompression sickness, is with pressure. And so one approach we have is, let's take the suit, let's stay in the suit in the airlock and take the airlock to 11, let's take the suit to 11 and use as much pressure as we can, as much oxygen as we can to try to squeeze those bubbles. That's our approach right now. The models say it works. It's never been tested. And then you get somebody, okay, let's treat them, they're back to go. When do they go out the door? Do you wait 1 day, 2 days, 3 days? Right now, we changed our standard from 72 hours to 24 hours. And then again, that was all purely based on literature review of diving. We don't know what it means in space. So with all these factors now we've talked about, now we can talk about how our transit pressure changes, how our different cadence changes, what exploration atmosphere it is. So again, all these factors are being traded back and forth. So you've now reached level 1, 2, and 3 of EVA treatment. So in summary, we know we have these 4 main legs to work in. When you pull one, the other ones shift around. And then there's all these other factors on, when you have not just your normal EVA, but what happens when you have an off-nominal EVA occur as well. Thank you. And if you have any questions, please feel free to ask right now or email me. Yeah.
That was really great. So thank you for that. Are you at the same time looking at novel or emerging monitoring parameters? Like, there might be case reports out there, for example, associating variability with DCS and early changes. Like, is that coming into play as both your monitoring capabilities increase as well as your concern for the astronaut?
Yeah, so the idea of how do you detect DCS before it happens, there's no blood marker or blood test or something you can say, oh, that's not, it's still a clinical, like, ow, it hurts, and if I increase the pressure, it goes away. It's basically most of the diagnosis. The only tool that's really being proposed to use is basically in-suit monitoring of bubbles. And so the idea is you put a Doppler monitor inside the suit, and the puck actually that I showed that we used was originally designed to be worn in the EMU. That hasn't really gone anywhere. Getting something in the suit is not as easy as it sounds. And also, when you put something, as you saw, when we're monitoring these bubbles, people are laying down, we're telling them to slow their breathing, and we adjust and we find the noise, and with the ultrasound we do that. We can't do that when you're walking out of a crater on the moon and be like, wait, hold on, lay down, let's get a good reading and everything. And so a non-disruptive measure of decompression stress is still hard to do. And the other thing too is, like, when we talk about personalized focuses of practice, like, hey, maybe Eric doesn't bubble and I bubble a lot, so do we do that? The Navy did a study. They found that the variability between divers is huge. So they have the same diver do the same dive every week, and sometimes they're a grade 1, sometimes they're a grade 4. Then the Divers Alert Network did a different study, and they found that actually, some bubblers tend to always bubble and some don't. So even in the diving world, which you'd think from medicine is like this big, but for us, when we're like this big in space, it's huge, and we don't know that from diving.
Can you just clarify, they've never actually correlated bubble density with clinical symptoms, is that true?
So a higher grade means more likelihood of DCS, but we're talking basically grade 0 is very low, less than 1% risk of DCS. A grade 1, I think, is like 4%. Don't quote me on the numbers, but something like 4%. Grade 2 is like 12%, and again, grade 4 is like 20%. But it really depends on the study. And Navy versus altitude Air Force studies completely differ. So we don't actually say, like, if you see 20% grade 3, what it means. Also, I mean, by flexing, you can take a grade 1 to a grade 4. And so some of these studies only looked at resting grades, some looked at flexing grades. So it's a little bit all over the place.
So just to follow
I think this will be the last question. Go ahead.
Sorry. So I just want to ask about the increased pressures decreasing the risk of DCS. But that also will impact the total output and work performed, because it's a lot harder to work in a higher pressure suit. So then you may need more EVAs or more time. So that, how does that factor into the mission timeline?
Yeah, absolutely. So if you think it's stiffer and it takes a lot longer to do a task, then you're doing it. What we basically did is we did a sort of back of the envelope calculation where we looked at if you use a 4.3 suit with a longer pre-breathe versus a 5.2 suit with a shorter pre-breathe, the workload penalty would have to be about 30%. So you'd have to be 30% slower to do a task to break even on the time. So that burden up front is huge, and it's also totally wasted time. So our goal is to try to basically get our cake and eat it and have a longer pre-breathe, but count it as EVA by doing it when you're walking. So if you're walking, remember, you're landing, you're putting all sorts of exhaust gases all over the moon. So the scientists are like, no, you want to go at least 2 kilometers out of here to get out of the nasty area and go into a shadowed region to go get samples. So that 2 kilometer, 1 hour walk, if we can do it with a higher suit pressure, where the suit basically supports itself, you're basically getting 1 free hour of pre-breathe with acceleration with workload, and you've made your initial traverse to your destination. So that's what we're trying to do is, that's what we call it working pre-breathe, where you're getting something useful out of it.
Cool. Thank you.
Thank you.